Day 614 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 1339, maximum product of splitted binary tree. The difficulty level is medium, so you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go in and check out that link in the description so you can get you some. Now let's see what the question says. Given the root of a binary tree, split the binary tree into two subtrees by removing one edge such that the product of the sums of the subtrees is maximized. Return the maximum product of the sums of the two subtrees. Since the answer may be too large, return it in modulo 10 to the ninth power plus 7. Note that you need to maximize the answer before taking the mod after and not after taking it. All right, y'all, so that may seem simple at first, but let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So in example 1, we have our input root equals an array of integers or binary tree. I believe it's a binary tree. Yep, or a binary tree. 1, 2, 3, 4, 5, 6. The output is 110. Explanation says remove the red edge and get two binary trees with the sum of 11 and 10. Their product is 110. So that's how we got the 110. So let's go ahead and break this down one step further, y'all, just so y'all can better understand what it is that's going on here. So right here we have our binary tree, right? And we need to remove one of these edges to create the maximum, so we can return the maximum product of the sums of the two subtrees. So they give us this edge right here in red. That's the one we're going to remove, right? So after we remove this edge right here, we're left with two subtrees, right? This 2, 4, and 5, and this 3 and 6. So that's this 2, 4, 5 right here, or excuse me, and 1, 3, and 6 right here because we removed this edge. So the 1 is over here. So we have 1, 3, and 6 over here. When we add these together, we have a sum of 11. 2 plus 4 is 6, plus 5, that's 11. Boom. Then 1 plus 3 is 4, plus 6 is 10, right? So boom. So this has a sum of 11. This has a sum of 10. When we multiply these two together, we get 110. Now, let's say we remove this edge instead, right? So say we kept this edge and we removed this edge. Then this would have a sum of 9, and this would have a sum of 1, 2, that's 3, plus 4, 7, plus 12. So it would be 9 plus, it would be 9 times 12, right? And 9 times 12 is going to give us, one moment, please. 9 times 12 is going to give us 108, see? So 108 is less than 110. So remember, we want the maximum, or we want the maximum product, right? And that's just one example. If we removed any one of these edges, the maximum product would still be less than 110. That's the point I'm trying to make. So 110 is the greatest product we can create if we remove any one of these edges. So that's why that's why the output is 110. Now, just in case that didn't make sense, let's take a look at example 2. In example 2, we have our input root equals a binary tree, 1, null, 2, 3, 4, null, null, 5, and 6. The output is 90. Explanation says remove the red edge and get two binary trees with the sum of 15 and 6. Their product is 90. So once again, same principles apply. So we have this binary tree right here. So we have the 1. So the null just means we have 1, we have a null on the left, and we have 2, right? So it goes 1, null, 2. So as you can see, there's nothing on this left subtree of 1. That's what null means. It means there is no left subtree. Boom. Then we have the 3 and 4. Boom, right? Then once again, we have this null right here that lets us know that the 3 has no children, right? No children here. That's one null. No children here. That's another null. And then we have the 5, 6, right? Boom. So that's just how the binary tree works. Now, what we want to do is remove one edge. So once again, they give us this edge right here in red. That's the one we're going to remove because we know that that is the one that we need, or is letting us know in this example that that's the one we need to remove to get the greatest output, which in this case is 90. So after we remove this edge right here, we're left with these two binary trees, the 1, 2, 3, and the 4, 5, 6, as they show us over here, right? So boom, now we have 1, 2, 3. When we add those together, we get 6. Boom. Sorry, y'all. Then we had the 4, 5, and 6. When we add those together, we get 15. Once again, 15 times 6 is 90, so that's how we got this 90. Now, just to give y'all another example, say we remove this edge instead and we kept this edge. Then we'd have a binary tree. This tree would have 1, and then this one would have 2, 3, that'd be 5, 9, 15, 19, and then that'd be 1 times 19, right? And then that'd just be 19, which is less than 90, and it'd be the same thing or something similar if we removed any other one of these edges. It would be less than the total product, or the maximum product would be less than if we remove this edge. So that's why this edge is highlighted in red, because that's the edge that we need to remove to get the maximum product. So now that we understand the question, y'all, let's get into the fun part, the actual solution. The solution is not that difficult at all. So let's get into it now. The first thing we're going to do is we're going to create a depth first search helper function, which will help us compute the sum of the subtrees rooted at root and append each subtree sum to the sums array. So for that, we'll come right here. We'll say func DFS, open up the parentheses, we'll say underscore root colon. That's going to be a tree node, question mark, then comma. Then we're going to say underscore sums colon. It's going to be an in out function. So we'll say in out, open up the parentheses, square brackets, and pass in the integer. So it's going to be an array of integers, and we are going to return an integer. Boom. Then we're going to open up the brackets. We're going to use a guard statement for our base case to see if an empty node. So if there's an empty node, so we're just going to say guard root equals root. Else we can open up the brackets and we can return. Sorry, y'all. We can return 0 just like that. Now we need to do our recursive computation to get the sum of the current node value plus the left subtree plus the right subtree. So we'll just come underneath this and we'll say let sum equal root dot val plus DFS, open up the parentheses, root dot left comma and sums, because when we're dealing with in and out, we have to put this and right here. And when we pass things in, then we're going to come outside of that, say plus DFS, open up the parentheses, root dot right comma and sums. Sorry, y'all. And sums. Boom. Then we need to store the sum of this subtree for later product calculation by coming underneath this. And we're just going to say sums dot append, open up the parentheses, sum, and we're going to return the sum to the parent. So we're just going to come right here and say return sum. Boom. Now we're not done yet. That's just the helper function. We need to still hook up this main function. So we need an array to store the sum of all subtrees. So we're going to create a variable called sums and set that equal to an array of integers. Come outside of that, put a parentheses to initialize it. Then we need to compute the total sum of the tree and populate the subtree sums. So we're going to say let total sum equal DFS, open up the parentheses, root, comma, and sums. Boom. Then we need to store our result. We could just come right here, declare a variable called result, and set that equal to 0. Now we're going to iterate over all subtree sums to calculate the max product. So we're going to come underneath this. We're going to say for sums, in sums, we're going to open up the bracket, and for each subtree sum, we're going to consider splitting the tree into the current subtree sum or the rest of the subtree, meaning the total sum minus sum. So we're going to say result equals max, open of the parentheses, result, comma, sums times, open up the parentheses, total sums minus sums. Boom. And then we're going to come right here and return the maximum product by coming right here. And we're going to say return result mod int, open up the parentheses, 1e 9 plus 7. Boom, just like that, y'all. So that should be all she wrote. Let's give it a run. Make sure it runs properly. Okay, cannot find total sums, so we need to remove this S. Let's run it again. Let's see. Okay, let's come down here. Cannot assign value of root is a let. So it should be guard let root. Sorry, y'all. So now let's run it. See if that did the trick. Let's see. It's going a little slow here. I don't know what's going on. It's accepted. There it is. So now let's go ahead and submit it. Make sure it's still accepted after we submit it. Let's see. Let's see. Let's see. Okay, okay. And look at that, y'all. 20 milliseconds beats 100% of users. That's what I'm talking about. That's what I like to see, y'all. So with that being said, make sure you get one more look at the code. This is the whole code right here. Boom, y'all. And yeah, I hope y'all learned something today. And I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.